Okay, so last section we're going to take a look at is 11.2. We'll split it up into 2 days, and it's on what's called a series, which I just said earlier. A series is when you add up all the numbers in the sequence. Okay? So a lot of times we're going to want to try to figure out shortcuts. Okay? If you've got 10 things to add up, that's not bad. 1,000 things to add up, we want a shortcut. So we're going to try to look for shortcuts to add up a bunch of numbers. So in the last section, we used this notation, a sub n, to represent a sequence. Sequence is always, or at least in our book, it's named with a lowercase letter. So I'm going to talk a little bit about sequence A. So I'm going to show you something, and I'm going to use this sequence formula. A sub n is 2n minus 1 squared. So that means if you want to know the first term, plug in 1 for n. If you want the second term, plug in 2. Third term, 3, and so on. So let's write out some of the terms in the sequence. And Myler, if I plug in 1, what's 2 times 1? 2, take away 1, and then squared. 1. So the first term in that sequence is a 1. Casey, if I plug in 2, what's 2 times 2?
4.
Minus 1?
3.
Squared?
6. Oh, sorry.
9. So there's the second term in that sequence. Third term, 2 times 3 is 6, minus 1 is 5, squared is 25. And let's do one more. Fourth term, 2 times 4 is 8, minus 1 is 7, squared is 49. So you can kind of see the pattern. It's a list of perfect squares, but it skips every other one. So you've got 1, you don't have 4. You've got 9, you don't have 16. You've got 25, you skip 36. So it's skipping every other perfect square. All right, so there's our sequence. Now we're going to add up some of these numbers that I just wrote down. And the notation we're going to use is capital S sub n. What that means is the sum of the first n terms. So S sub 1 would mean take the sequence that we have and add up the first 1 terms. Well, if you add up the first 1 terms in that sequence, it's just the first term. So S sub 1 is 1. I had some of these written, but I want to do them out with you. S sub 2. That means to add up the sum of the first 2 numbers in our sequence. So we have a 1 plus a 9, 10. S sub 3 means to add up the first 3 numbers in that sequence. So now we have 1 plus 9 plus 25. 1 plus 9 plus 25. And if you add up 1 plus 9 plus 25, you get 35. Any questions on how I'm finding that? All right. So that's, not worried about that. So that's what that notation means. S sub 1, S sub 2, S sub 3. You're adding the first n terms together. So now, if you wanted to find, say, S sub 50, well, unless you're going to find all 50 of these numbers, doing it this way is going to be a real pain. So 1, 10, 35. Now what I could try to do, and I'd probably need another one, but is look for a pattern here. 1, 10, 35, and try to predict the next sum based on the pattern of the sums before it. Okay? That's the goal what we're gonna try to figure out. Maybe not for this one, but easier ones in the future. All right. So each thing that I just found, let me try to put it back up. S1, S2, S3. These are called a finite series. Finite means you added up a certain amount of things. Finite means it does not go on forever. S sub 3, 1 plus 9 plus 25. That's it. Even if I did S sub a million, that's still finite. It might have a million things added together, but at some point it ends. It ends at the millionth term. Okay. Okay, so S sub n is called a finite series because you're only adding up a finite or a certain amount of numbers. Any questions why those are called finite sums? An infinite sum would almost have a dot, dot, dot. That would mean you're adding up every number to infinity. For a pattern like this, it wouldn't work. Because look at what's happening. 1, 9, 25, 49. They're just getting bigger and bigger and bigger and bigger. Okay? If you tried to add up every number forever in this sequence, you'd just get a huge number. It would just keep getting bigger and bigger. Right? So this is not the kind of sequence we could look at and add up forever. All right, so suppose we had some sequence, just like we had here, and it's generating terms, 1, 9, 25, 49. If you then take the partial sums, 1, 10, 35, and write them like this. And it keeps going. We didn't do the next one. What you're writing right here, 1, comma 10, comma 35, that's called a sequence of partial sums. It's a new sequence because it's separated with commas. And each number in the sequence represents adding up a bunch of other numbers. Okay. So when you're finding your first partial sum, there's not much to add up with S sub 1. S sub 1 means find the sum of the first number. There's only one number. S sub 2 means find the sum of the first two numbers. Okay. S sub 3, find the sum of the first three numbers. S sub 4, add up the first four. We did these three right here for this specific sequence. We got 1, 10, 36. 35. If you wanted to know S sub 4, it would be 1 plus 9 plus 25 plus 49. That would be the next number in that list. Okay, question on that idea? Okay, and you can go as high as you want. So this last one represents the nth partial sum. For today, n will be fixed. Maybe you'll have to find the 5th, the 6th, the 20th, the 25th, but there will be a stopping point to what you're adding up today. And when we do the problems, if it starts to get really high, like you have to add up 50 things, you're not going to add up 50 things by hand. It's going to take too long. You're probably going to make a mistake. So there's got to be a shortcut for doing these out so we don't have to do it this way every time. Okay? Because I don't want to sit there and add up 50 things to find the 5th partial or the 50th partial sum. All right. So the first thing I'm going to show you, it's not a shortcut for calculation. It doesn't speed up anything at all in terms of a calculation. What it does give you is a short way to write things down on paper. That's all it is. So it's not a speed improvement for calculating something. It's just a short way of writing things on paper. But you still have to do the whole thing out. Okay? But the short way of writing it is called sigma notation. And sigma is a Greek letter, and the notation is going to use a capital Greek letter sigma. And I'll show you what it looks like. So let's say you had a sequence, and you wanted to add up terms 1 to n. Maybe it's 1 to 10, 1 to 50, 1 to 1,000, but you want to add up the first n terms. Okay, whatever number somebody picks for n. This is how you could write it down. Okay. To do it out, it would still be a pain, but to write it down, you can use this notation. So the notation really has 4 parts to it. First of all, it has that Greek letter. It looks better on the left. The one I drew on the right is a little messed up, but the one on the left looks better. As I start writing them fast, they start really looking pretty bad. But I'll try to make them look neat. Okay. Here is a formula that's generating the terms of your sequence. So that thing I just circled, that's the stuff you found in last night's homework. That's an explicit formula for the terms in a sequence. The number at the bottom tells you what's the first term you want to add up in the sequence. If you put k equals 1, then that means you're going to start with the first term. If I did something like this, that means forget the first term. We're going to start adding things up, but we're going to start with the second term now. We're going to skip the first one. All right, so whatever number you put here controls where you want to start adding things up in the sequence. That's where you want to stop. So if you made that an actual number, like leave it as n in your notes, but let's say you put an 8. What this would mean is, in the sequence A, add up all the terms from 1 to 8. That's what the notation means. It's not a fast way to do it. It's just a fast way to write it. If I didn't have that notation, and I wanted to write this out like that, adding up all the terms from the first term to the 8th term, I would have to write this. First term, plus second, plus third, plus fourth, plus fifth, plus sixth, plus seventh, plus 8th. What I just wrote right here is shortened by writing exactly what I just put right there. So I'm going to put it back the way I gave it to you in the notes. If you wanted to pronounce that, that means the sum. So you start by pronouncing the sigma. That means sum. The sum starting from the first term all the way up to the nth term of, and they'll give you a sequence. K, that thing at the bottom, that's called the index of your summation. The index, basically, it just controls what term you start with. That's all. And a lot of times k equals 1 is pretty common. We usually start with letting 1 be the first term. Okay, so let's look at this one. This problem is asking for the 5th partial sum. So that means we're going to add up 5 things. So we have 5 calculations to do. They want us to use this formula, and they want you to plug in the number 1, then the number 2, then the number 3, then the number 4, then the number 5. 5 is the last number you're going to plug in for k. They want you to do each one of those calculations one at a time, and then add them up. So let's just kind of go through it and see what happens. So Evan, if I start with 1 for k, what's 2 times 1?
2, 5.
Plus 3? 5. That's the first one. Plus, now we do the second one. Plug in 2 for k. 2 times 2 is 4. 4 plus 3, 7. Now we plug in 3 for k. 2 times 3 is 6. 6 plus 3 is 9. Plug in 4 for k. You get 11. And now you keep going until you hit this top number. Now we plug in 5 for k. 2 times 5 is 10. Plus 3 is 13. Now you wouldn't do 6 for k because it didn't say to go to 6. It said stop at 5. So if you add all that up, that's what S sub 5 equals. Any questions on that? That idea kind of makes sense? Again, it's not a speedy way to do anything. You still have to do everything out by hand. It's just a fast way to write it, especially if you wanted me to write S sub 1,000. All I would have to do is change that to 1,000. There you go. Now to do it out, it would take forever. But I can write how to do it very quickly. Okay, when you write something in that notation, that is called sigma notation. So, what I have on the left, circled in red, that's sigma notation. What I have on the right, circled in black, that's expanded notation. Expanded notation is when you actually do it out. Okay? So in this problem we just did, the left is sigma notation, the right is expanded notation. Okay. Any question on the difference between the two there? We actually already did this, but, well, we did something similar, but we'll go through this one too. So when they ask you to expand this and they don't tell you where to stop, what I usually do is I just do out the first 3 and then put a dot, 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 and then jump to the last one. Okay, because we can kind of see the pattern if you just do out a few of them. Okay, so Andrew, what number am I starting with here?
1.
1. So if we plug in 1, what's 2 times 1?
2.
2 plus 3?
4. 4 squared, 16.
Careful, slow down. 2 plus 3?
5.
Squared?
25.
25. 25 plus, Josie, what's the next number I plug in for k after 1?
Just do the next 2.
2. So now 2 times 2?
Oh, you're asking before.
Yeah.
Sorry.
Plus 3?
7.
And then we square it?
49.
49. Plus, let's do one more, and then we'll go to the last one. Josh, after 2, what do I plug in for k? 3. 2 times 3?
6.
Plus 3?
9.
Squared?
81.
81. Now, what I'm going to do is put dot, 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 plus, and what's the last thing I would plug in for k? Even though it's not a number in this case. N. N is some fixed number. We don't know what it is, but n is the last one. So now plug in n. 2 times n plus 3 squared. So that's the first term, second term, third term, nth term. Okay, but the point here is there is no dot, dot, dot after the 2n plus 3. It ends there. When you replace n with an infinity symbol on the top, then it goes on forever. Okay, we're not looking at that today. Okay. Any questions on expanding the sum? Okay. So let's look at some different properties we can use to do something like that. We can take 2 summations that are separate and combine them together, and you pretty much do it exactly like you would think. You combine like terms. Okay? It's really pretty straightforward. So here's our first one. It kind of looks like distributive property. Okay, kind of. If you have the sum of 2 different sequences, okay, that's what this is saying. You have 2 different sequences, and you want to add them together. You can do it two ways. You can add together the individual terms first and then add everything up, or add the entire first sequence up, add the entire second sequence up, and then add those two results. Okay, so I'll make up two really simple sequences just to show you with a very small amount of terms. Let's let sequence A be the numbers 1, 3, 5. Okay. Let's let sequence B be the numbers 2, 4, 6. And that's it. So it's just two sequences. They each have 3 terms in them. Now, on the left, it says to do this first. Take sequence A and sequence B and add them up term by term. So let's do it. 1 plus 2. I'll just put it right here. 1 plus 2 gives me a 3. 3 plus 4 gives me a 7. 5 plus 6 gives me an 11. Any questions on what I just did? So I just added up the sequences term by term. First ones, second ones, third ones. 3, 7, 11 is what's right there. Now, the next part says, take the numbers you just got when you added them, the 3, 7, and 11, and now add those up. That's what this symbol means. Add them up. What's 3 plus 7 plus 11? 21. So using the two sequences I have, following the formula on the left, that's how you do it. The one on the right is a little different. First it says, forget about sequence B. Just look at sequence A and add everything up in sequence A. So what's 1 plus 3 plus 5? 9. Plus. Now it says, forget about sequence A, just add up what's in sequence B. 2, 4, and 6. 12. What's 9 plus 12? 21. So no matter which way you do it, you get exactly the same thing. That's what I'm just trying to show you. Okay? I'm not going to do that out for every rule we have. But the same exact rule works with subtraction. You could subtract them term by term, or you could do it the other way. Okay, but it works. What I would probably do, if you didn't want to write the same rule twice, you could just put a plus or minus like that. And then that covers rules 1 and 2. Or write it all out again separate. It's up to you. Okay, and the third rule, and the last one, has to do with multiplying a sequence by a constant. So what you're allowed to do is you can put a number here, or you can put it in front. It'll be easier if I just show you a really quick example with numbers. Okay, so sequence A, I use the numbers 1, 3, 5. Okay, so let's use those same numbers again. 1, 3, 5. And let's let C equal 2. So on the left, what it's saying to do is to take C times every number in your sequence and then add that up. So let me do C times every number in my sequence. So C is 2, and my sequence is right up above. So basically just double every number in that sequence. 2, 6, 10. That's what you get if you take C times the numbers in my sequence. Yeah?
Why did you use 1, 2, and 5?
I just made up.
Oh, so that'd be like a given?
Yeah, I just made up a very short, simple sequence with 3 very simple numbers. Yeah. So I took every number in that sequence, multiplied it by c. Why did I pick 2 for c? It's easy to multiply a number by 2 in my head. C could be anything. Now, I have this. Now, this symbol means add them up. 2 plus 6 plus 10. What's 2 plus 6 plus 10? 18. Okay. That's what you get if you do it the way on the left. Now, on the right, it says, forget about c for now. Add them up first, and then multiply by c after. So let's add them up first. Sequence A. What's 1 plus 3 plus 5? 9. And now, put the c in front of the calculation you just did. C is 2. What's 2 times 9? 18. 18. So it's just 2 different ways of doing exactly the same thing. That's what I'm trying to show you. Okay, it looks a little confusing because it's a notation you haven't seen before. But I think if you break it down with numbers, it's not as bad. So any questions on those 3 rules? Now we'll go through a couple problems and I'll show you where they actually, how they're used. And it's going to be a little easier because everything is going to be numbers. It's not going to be as abstract as this. All right, so here's an actual problem. The first thing to look for, if you want to take 2 different sigmas and combine them into one, they have to start at the same spot. They have to end at the same spot. I'll never give you ones that don't. In calculus, you do. You have some that don't start and end at the same spot, so you have to fix that first. But here, they start at 1, they end at n. So when you combine this into a single sum, we're going to use the first rule right here. They both start at 1, they both end at n. So when I combine them together, it's going to start at 1, it's going to end at n. I'm just copying that over from the ones on the right. So start at 1, end at n. Now, let's go back and look at the rule. Take the terms in the first sequence. That's 5k squared minus 4. Take the terms in the second sequence. That's 7 minus 2k plus k squared. And add them together. So take the first sequence terms, the second sequence terms, and add them up. So now we just combine like terms. 5k squared plus 1k squared is how much? 6k squared. So we took care of that and that. I have a minus 4 and a positive 7. 3. I'm going to put that, it's a plus 3, put that at the end. And what's the only thing left? I didn't have anything to combine it with. So you still have to put that down right here. So I think the rules themselves, they look a little confusing, but when you actually go and do it, it's just combining like terms. And that's it. Any questions on that? All right. Does anyone need to see another one like that? That's the only one I was going to do. But. Okay. So I've said it before. Sigma notation is a really short way to write things down, but it doesn't actually save you any time. To do the whole thing out, it's going to take a while. So let's say you wanted to know what that is. What this is doing is it's giving you a very simple formula. It's not like it's 2k or 5k plus 1 squared. It's just a k. So you plug in 1 for k, you get 1. Plug in 2 for k, you get 2. Plug in 3, you get 3. Plug in 4, all the way up to 10. So if you wanted to do this out, you would still have to add up every single number from 1 to 10, which isn't bad, but imagine you had to add up every number from 1 to 1,000,000. Now it's going to take a little longer. But because that's a pretty common problem, just adding up integers, there's a formula to do it. Okay, and I'm going to show you what the formula is. Most of these formulas are not formulas you can really figure out easily or guess. A lot of times they're formulas, if you need them, you look them up in a book or you find where they are. Okay, you would not be figuring these out by hand. Let's take a look at some formulas. All of these formulas are on page 593 in your book. I think the book does more formulas than I'm going to give you. Whatever I don't give you on the board, you don't need. Okay? Because we're not really doing everything that's in the book. So let's look at the first one. It says the sum from k equals 1 to n of a constant. That's a constant. So a problem like that could be, let's say you had something like from k equals 1 to 4 of the number 3. Notice there's no variable here. There's no spot to plug a k into. So when you try to plug k, well, I'll start with 1. When you plug 1 in right there, what do you get? You can't plug it in, so what's there right now? A 3, so that's what you get. If you plug in 1, you get a 3. What if you plug in 2? You get a 3. What if you plug in 3? You get a 3. And now it says to stop at 4. What if you plug in 4? You get a 3. How many times did you get a 3?
4.
You got a 3 4 times. 3 times 4. You got a 3 4 times. C times n. So that's where that comes from. Okay? So that's an example of just adding up a constant over and over. There is no formula. You're just adding up the same number n times. And when you add the same thing over and over, we call it multiplication. Okay, the next one is the formula that I mentioned just a minute ago. This is how you can add up the first n integers by hand. And we'll try it. So it's n times n plus 1 over 2. So let's take the first 5 integers. 1, 2, 3, 4, 5. Now, in theory, if I plug 5 in for n, I should get the answer that I'm about to get right now. 1 plus 2 gives me 3. 3 plus 3 is 6. 6 plus 4 is 10. 10 plus 5 is 15. So if you add up the first 5 integers, you get 15. Now, let's try the shortcut. Let's plug a 5 in for n. What's 5 plus 1? 6 times 5? 30 divided by 2? 15. So now, if you wanted me to add up, say, the first 20 integers, I'm not going to add up 1 plus 2 plus 3 all the way up to 20. I'm just going to say 21 times 20 divided by 2. Whatever 21 times 20 divided by 2 is, that's what I would get if I added up the first 20 numbers in a row. Okay? So it's a nice shortcut. Okay. Here's a shortcut for adding up squares. Okay. perfect squares. Okay, perfect squares would be like 1, 4, 9, 16, 25, 36, and it keeps going. So that would even be a little harder for me to do because the result would be a lot bigger. So this is 1, 2, 3, 4, 5. I wrote out the first 6. So if you wanted to add up the first 6 perfect squares, you would add those numbers up on your calculator. Or just plug a 6 in for n in that formula. So you get 6 times 7 times 13 divided by 6. That's a lot easier calculation to do than adding up 6 numbers one at a time. Okay. There's also a formula for adding up cubes. You don't need to know the cube one. We're not going to do that one. Okay. So just up to squares. In fact, you can come up with a formula for anything you want. Anything. Okay. If it's used often enough, somebody already has a formula. Someone already figured out how to do it, so you don't need to figure it out. Honestly, this one I could figure out by hand. That one's pretty easy. This one I do know how to figure out by hand, but beyond that, it gets kind of hard to figure these out. I don't know how to figure that one out by hand. I would just have to look it up. And obviously anything after that is even harder. Okay. Any questions on those 3 formulas? All right. So I want to simplify that. It's the sum from k equals 1 to n of negative 2k plus 3. So the way to do this is to separate it using, where's the rule? Right here. If you have 1, separate it into 2. Okay, 2 separate problems. So that's going to be my first one. That's going to be my second one. So we're going to have 2 of these. They're both going to start at 1. They're both going to end at n. That never changes. You don't even have to worry about the k equals 1 and n. You just copy those down. The first one is negative 2k. The second one, plus, here's my plus, 3. Okay. Any question on that part? We're just splitting it into 2 problems. All right. Next thing. I have a number right there in that spot. Go back and look at the third rule. When you have a number in that spot, where are you allowed to move it? To the outside. You can put it in the front. Right there. So move that number to the front. And then I'll show you from there why we did this. So negative 2. And you have the sum from k equals 1 to n of k. Look at that very closely. What's in that red box? The sum from k equals 1 to n of k. The sum from k equals 1 to n of k. I can already tell you what that equals. It's right there. That's why we did that. So your goal when you're doing this is to get something that looks like this, looks like this, or looks like that. You want to get one of those 3 things, and then you already know what it equals. So we're trying to get rid of these Greek letters. That's the goal of this problem. Get rid of the Greek letter thing. Okay. The second one, just copy it down. Now, if you look at that and you're like, wait, where is that? Well, that's the sum from k equals 1 to n of a constant. In this case, the constant is a 3. That's right here. K equals 1 to n of a constant. So I'll put these on the board at the same time. Let's see if we can substitute in. So first thing is the -2 is just going to hang out in front. Nothing happens to the -2. But let's look at that red box. K equals 1 to n of k. That's right here. K equals 1 to n of k. So I'm going to change that sigma to n times n plus 1 over 2. n plus 1 over 2. Now the sigma is gone. It's gone, completely gone. I don't have it anymore because I changed it. Basically, I did a substitution. That's what I did. Okay, let's look at the next one. It's the sum from k equals 1 to n of 3. So in that second red box, C in my problem is 3. So what would be the formula for the second box is around? 3n. 3, that's my constant, n. Now we've gotten rid of all the sigmas. Now we just have to clean it up and make it look a little nicer. If you want to think of -2 as a fraction like that, it might be easier. 2 in the top, 2 in the bottom. Anytime you have the same number in top and bottom of a fraction, it cancels. Now we have a negative and an n on the outside. So distribute it. Okay. What's negative n times n? Negative n squared. And what's negative n times 1? Negative n. And the plus 3n, we didn't do anything with it yet, but we can combine. What's negative n plus 3n? 2n. And that's the answer. Okay, so the goal, again, is to get the sigmas by themselves. Okay? And you'll never have one that's really any worse than that. And then plug in using the formulas. Okay? In fact, I gave you the formula for squared. We're probably not even going to use squared. We're just going to stick with the first one and the second one. Okay? So cubed, you can totally forget. I told you don't even copy the cubed one down, but probably not even going to use squared. I think I have one more of those. Okay, let's try this one, but I'm going to change it. I'm going to get rid of the squared term. Just move that a little closer. So it's the sum from k equals 1 to n of 5k minus 2. First of all, when I split this up, how many sigmas does this split up into? 2. The first one is 5k. The second one is just a 2. So the 5k got copied down. The minus sign, that's what goes between them, because it was what was between them up above. And then the 2 just got copied down. Now, without rewriting it, so I don't have to do it all again, where can I put the 5?
On the outside.
Put it on the outside. If you want to write this as a whole separate step, you can. Now, we just did that. The sum from k equals 1 to n of k is right here. n plus 1 over 2. So replace what I just circled in red with n plus 1 over 2. But what's still in front of all that stuff I circled in red? Still have a 5 in front of all that stuff. So you can just put a 5 right there. Minus. And what about when I replace this with that.
Minus 2n.
Minus 2n. Yep. And now from here, we just have to kind of clean it up a little bit. Distribute that out just like we did before. 5n squared plus 5n. And now that's all divided by 2. So I can write it two different ways. I can put it all divided by 2, or I can do it like this. Put each one separate divided by 2. Now this part might be a little tricky without a calculator. What's 5 halves as a decimal? 2.5. So you have 2.5n take away 2n. What's 2.5 take away 2? 0.5. So 5n squared plus 0.5, or plus a half n.
You have to divide 5 and by 2 as well. You have to divide that by 2. 5 squared.
Oh, yes, thank you. Yes, don't forget that. It's still over 2. We didn't change that. Yep. Okay. Any questions on? All right, so last formula. So this is a formula for adding up terms in a geometric series. So let's say you had something like 2, 4, 6, 8, actually. That's a geometric series. The reason it's geometric is because I'm multiplying each time to get from one term to the next. What did I multiply by each time?
So
2. Yeah, I doubled each time. So in this problem, r is 2. What was the very first term in this sequence? It was also 2. And how many terms did I write down on the board? 6. If you want to know what all those add up to, without doing it by hand, plug in a 2 for r, plug in a 6 for n, because we had 6, and plug in a 2 for the first term. And that formula will tell you what they add up to. Now, honestly, to add these up by hand, it wouldn't be that bad. But let's say I continued this pattern for 200 terms, and I wanted to know what did the first 200 add up to? Well, all I would have to do is let that be a 200. R would be 2, and the first term is a 2. Okay, so we'll try that. I'm not going to use that example, but we'll finish up with one that's similar. Okay, so here's a pattern, and I want you to add up the first 12 terms in this pattern. If you are finding all 12 and doing it by hand, you're not doing it the right way. Because I might give you one on the test that says add up the first 100. You're not going to be able to list out all 100. Use this formula. What's the first term in that sequence? 2. R, that's what you multiply by each time. What do you multiply by each time there?
third.
A third. 2 times a third is 2/3, times a third is 2/9, times another third would be 2/27. Okay. Multiply by a third. And now n is how many terms you want to add up. The directions tell us to add up how many? 12. Okay. So just plug those numbers into those spots and see what you get. So if you were to list out all 12 terms in that pattern I just showed you and add them all up, you would get 2 times 1 minus 1/3 to the 12th all over 1 minus 1/3. Okay, so let's see what that adds up to. All right, let's not use that one. Let's use this one. Okay, it's a little messy to type in because you got a few sets of parentheses, but
Wait, why?
it's not super bad. Yep.
Never mind.
All right. So I've got, you know what, I'm going to forget about the 2. I'll do the 2 after because it's just too much stuff for me to type in. Let's do 1 minus 1/3 raised to the 12th. Okay, so there's the top. Divided by 1 minus 1/3. Now I know 1 minus 1/3 is 2/3, so I could just do it that way. But if I'm not sure, just type it in like that. So that's the bottom, and that's all multiplied by 2. So if you add up the first 15 terms in this pattern, it's 2.999999. This is an example of a pattern that if you added up the first 1,000 terms, it wouldn't be much different than that number. What do you think this sequence is approaching? It's approaching 3. If you added up the first 1,000,000 terms, it might say 2.9 100 times and then a different number. But this sequence will never add up to more than 3, and the first 15 kind of shows you that. All right, so you could write your answer here, S sub 12. It's about 3. Okay, and that formula only works on a geometric series, not arithmetic, but geometric. Okay, so on your reference sheet, make sure you put down that's geometric. All right, so homework tonight is on page 601, and it's 1 through 19 odd. Okay, 1 through 19 odd.